In this problem, we're going to investigate the premise that driving faster over a washboard road is going to give us a smoother ride than if we are driving slowly over that same washboard road. We're going to approximate the shape of the washboard road as a sinusoidal curve. So we're going to have peaks and valleys that are going to be regular. And we're going to assume that the wavelength, or the spacing between the peaks, is going to be constant. So what we want to look at is what's the response of the car as we go over this washboard road. The washboard road is going to act as a prescribed displacement on the bottom of the tires, and then that displacement is going to be transferred up to the cabin of the car. So we want to assess what is the displacement of the cabin as we go faster or slower over this road. So where we can start here is we're going to be making a model of our car, and we're going to be treating the car using what we call a quarter car model. And as the model implies, we're going to split the entire car into quarters, and we're going to model just what a quarter of the car is doing, like we see in picture A. Now, part of this assumption is in the quarter car model that the entire car is going to only translate vertically. Now, in a real car, if we used a more extensive model, like a half car model, we would allow the car to pitch and have some angle of rotation. And if we used a full car model, then we would allow the car to pitch and to roll. And it would have 3 degrees of freedom. So we're constricting it to just a single degree of freedom, which is not the most accurate, because if the front wheels and the back wheels are not at the same point in the washboard road, like both at the peak or both at the valley at the same time, then we're certainly going to have some pitch in the car that we are assuming away. But this constricts it to a 1 degree of freedom model that we're able to handle. In our quarter car model, we're going to have a mass of the quarter of the car sitting on just one piece of the suspension, which is going to have our spring and our damper. However, the ground now is going to be capable of moving as well. So we are going to define here the vertical motion of M will be, I'll say, positive up with X, and then the platform it's sitting on, I'm going to define as positive up with Y. So the platform can move, or the base, that's really the ground, is able to move up and down from some baseline, and that's going to transfer through the spring and the damper into our mass. So in reality, there is going to be a force acting on the mass, but the force is coming from the difference in displacement and the difference in velocities between the ground and the cabin of the car. So in our model, since we're using a quarter car, if the vehicle has a total mass of 1,500, that means the mass of our total car, if we're distributing it evenly, is going to be a quarter of that. So 375 kilograms is what our quarter car is doing. And the total spring constant of the full car, since we're assuming that the full car can only move in a vertical direction, that means that the suspension system would be in parallel. So also we need to quarter the spring constant. So it will be 400 kilonewtons per meter over 4. So that is going to give us 100,000 newtons per meter. I'll work with base units. So again, we're assuming that each tire would have 1/4 of the suspension. So if each of the 4 wheels has 100,000 newtons per meter, since they're in parallel, we can add it together, and that's how we get that total spring constant for the vehicle of 400,000 newtons per meter. And we're told the damping ratio is 0.3. So we're actually going to have to kind of jump around a little bit here into what would usually be this parameter step now to know how this system is being put together, so we can kind of jump back into what's typically in the model, because the C would usually go into the model, but we are told about the damping ratio. Now, we know what our model is going to look like. It's this 1 degree of freedom system, and it's going to be damped, and we're told, since zeta is 0.3, that it's underdamped. So we can actually jump right here and say that zeta is 0.3 is C over 2m omega n. And actually, before we get to solving for zeta, we can solve for the natural frequency. So we know for the quarter model that the K is 100,000, and we know that the M is 375, and this is all base units now, newtons, meters, kilograms. So the natural frequency of, well, the full car or the quarter car, they share the same natural frequency since we quartered the mass and we quartered the spring constant. For either the quarter or the full car, our natural frequency is about 16.3 radians per second. Now we can put that information up here with our damping ratio. So 2 times the mass of the quarter car is 375 times omega n is 16.3. And out of that, we can get our damping coefficient for the quarter car is going to be 3.67 times 10 to the third Newton seconds per meter. And I'll copy that up here as well. So we can identify what we have, which really we're already told what the type of system is that we have. I'm probably not going to make the actual equation of motion out for this because it is this prescribed displacement, but we are told to treat it as a quarter car, so that makes it 1 degree of freedom. It is going to be linear, and we are going, it's forced, but the type of forcing is going to be a prescribed displacement, which makes our solution just that a little bit different. And by the nature of the zeta, it is underdamped. So I'm actually going to continue with the parameter section because we know we're going to need some certain other parameters in order to find the steady state response of the system. So that's what we want in part A, the steady state response. When we're going at a specific vehicle speed, 10 kilometers per hour, then we want to generalize it and see what's the response as we go faster or slower. What's the cabin going to be doing under those circumstances? So looking at the parameters we're going to be needing here, for the particular solution, we need the amplitude, we need the phase. The amplitude x is going to depend on the amplitude of the input displacement, y. The k, the c, and the driving frequency. The driving frequency we don't know yet. So we're going to need y and we're going to need omega in order to calculate x and phi so that we can put those together to get the steady state response. So the value of y is going to be given to us. If we look back at the prompt, we are looking at this washboard road, and the washboard road is going to have an amplitude of 0.05 meters. And we're not given the angular frequency of the washboard road, but we are told the wavelength is 0.5 meters. So we're going to need to use that information to get our angular frequency. If we think back to physics 1, maybe physics 2, when talking about wavelength and talking about angular frequency, we know that the angular frequency can be calculated using 2 pi times the wave speed over the wavelength. So again, we're given the wavelength, base units, 0.5 meters. We have 2 pi on top. So we have to look at our wave speed, at least for part A, to begin. So in our model, we have our quarter car, and presumably in picture B, it's moving to the right over this washboard road. We can also think about the situation kind of inverted, where the car is stationary, but we are dragging the road to the left, and then that bottom of the tire is going to be going up and down, connected to the surface of the road. We're assuming that the tire is going to always maintain contact with the surface of the road. So how fast that wave or that ground is being pulled to the left is going to be our wave speed. But that's exactly the same idea as if the car is moving relative to our wave, and that's the vehicle speed. So this 10 kilometers per hour of the vehicle is going to be the wave speed. That's relatively how fast is that wave traveling to our stationary object, even though the object is actually the thing in absolute terms traveling over the wave. So our V was once again, for part A, 10 kilometers per hour. But we want everything in our base units here. So 1 hour is going to be We want this in seconds, so 60 squared seconds. And we have kilometer is 1,000 meters. And then the wavelength was already in meters. Right, so our hours are going to go away, our kilometers are going to go away, and now we're going to be operating in our base units. So we can calculate the angular frequency of this wave, of this washboard road, is going to be 35 radians per second. Using this information, the capital Y and the omega, we can calculate the transmissibility. First, I'll do that. That's our x over y. So from these slides, we know that this is going to be our k squared plus c omega squared, the square root of that, over the square root of k minus omega squared m, quantity squared, plus quantity c omega squared. And if we put in the k, which we now know, the c, which we know, the omega, which we just calculated, we are going to find that the transmissibility is going to be 0.43 when we are traveling at this 10 kilometers per hour. And we can find our phase as well. So we want to use the 4-quadrant arctangent here of mc omega squared over k minus m omega squared minus c omega squared. Again, at this point we know all of those values, so just plugging everything in, we get a phase of 1.88 radians. Now we can assemble our solution because we know what it should look like, at least the steady state solution. So at steady state, or the particular solution, is going to be our x times sine omega t minus phi. Our x we can calculate, now that we know the transmissibility, if we multiply y by the transmissibility, we're going to get x. So our steady state, we get 0.021 sine 35t minus 1.88. Now in this case, our transmissibility was 0.43, so that is telling us that the cabin is going to move 43% as much as the ground. So we in the cabin are going to experience less displacement than the tires do, about half as much of the displacement. Now we can go into the MATLAB and we can graph what the response of the cabin is going to look like on this washboard road. So putting in all of the pertinent information that we already solved by hand. And we'll come back to the transmissibility in a moment. First, let's just plot the response of this system when we were going at the rate of 10 kilometers per hour. So we can calculate our x, and we can calculate our phi, as we've already done. And let's look at what this does over 5 forcing periods. So that's 5 times the 2 pi over the omega will give us 5 forcing periods. So the black line is our x of t. That is the vertical displacement of the cabin of the car. And the red is the y of t. That is the displacement of the ground. That's the displacement of that washboard road. So I'm doing everything here in base units. So we see again the tires are going to go from kind of the baseline. It's going to go up by 0.05 meters and then down from that baseline by 0.05 meters and up and down, and that's that repeating pattern of the washboard road. And we see the cabin is experiencing about half of that. Well, we already knew the transmissibility was 43%, so it's 43% as much displacement while we're riding in the car as what the tires are experiencing on the road itself. So that addressed the first part. If we're deciding to go at 10 kilometers per hour, what's the displacement going to look like? But more generally, let's look at the transmissibility as a function of our vehicle velocity. So this gets into the question, does going faster over a washboard road actually give us a smoother ride than if we go slower? Which seems a bit counterintuitive. We think if we go faster over it, we should actually experience a bumpier ride. So let's see if this is the case mathematically according to our model. So what we're going to relax now is in this transmissibility is really what we're going to care about here. In the transmissibility equation, what happens if we let omega change? And we already know that omega is going to be the 2 pi v over lambda. So lambda is going to be constant. We're not changing the actual washboard road. We are going to allow v to vary, which is going to make omega vary, which is going to make our transmissibility vary. So I've set up here in 216, I am defining my transmissibility TD in terms of omega. So for every omega, I'm going to be able to calculate a new transmissibility. Now, what we're going to find is specific to this vehicle. It's just we're going to allow this specific vehicle to go faster or slower and see what the transmissibility curve looks like. Right, so I'm going to try various speeds from 0 to 30 kilometers per hour, since that's the form the speed was given to us in. I'm going to take that, so that's what I'm doing in the v-test. Those are the test velocities. So faster than the 10, slower than the 10 as the baseline that we just looked at. Then I need to convert those into angular frequencies, which we did in the previous problem, but now I'll do this all at once. So I'll put each of those velocities, angular frequencies that they become, into the transmissibility equation and plot it, and we'll see what those results are. So here are our results, and I actually have it in two kinds of units, kilometers per hour and miles per hour. Miles per hour is probably going to be a little bit more intuitive to us while we're driving a car, but all it's changing is the x scale. Everything else is going to be the same. So if we let's look at the miles per hour here. So it's a 1 degree of freedom system, just like we saw with prescribed forcing. So we're going to expect similar results to what we see with prescribed forcing, that we should have this peak magnitude, and the faster we go, like in other 1 degree of freedom systems, actually that magnitude, in this case transmissibility, is going to go down. So for this car over this particular road, we see kind of the worst case scenario is when we are going, well, actually pretty slow, 2.7 miles per hour, we're seeing a transmissibility of almost 2. So that would mean if we're going this slow over the washboard road, the cabin is actually going to have about twice as much displacement as the washboard road itself. So this is going to provide us a very bumpy ride if we're going this slow over this road. Now, if we look at our baseline on the left, that's when we're going 10 kilometers per hour. Our transmissibility was about 43%. And these plots, that is going to be miles per hour wise. We should see about, that's only going like 6 miles per hour. That's pretty slow. Now, it's a washboard road, so we would want to be cautious, but what we're seeing suggested from the transmissibility diagram, really this is a Bode diagram, but we're looking at transmissibility versus velocity, which translates to angular velocity. We're seeing that if we go faster, the transmissibility is going to go down further and further. So that y value, we're going down to only 12% when we're going 15 miles per hour. And I've only plotted it out to about 18.6 miles per hour, but that transmissibility is only getting lower and lower. So mathematically, and for our simple model, the myth or the suggestion that going faster over a washboard road is going to give us a smoother ride does seem to hold up. By going faster, the transmissibility goes down, so as a percentage of the road's displacement, the cabin is feeling less and less of that displacement. Now, as a caution, due to assumptions that we made, we are only looking at the steady state behavior of the cabin. We are not looking at the transient behavior. So when we're going in that transition between the flat road and the washboard road, we might at different speeds experience very different displacements during the transient phase than during the steady state phase. So we would want to look at this total solution of our displacement at various speeds, not just the steady state, before we decide it's a good idea to go faster over the washboard road. Also, our only judgment of smoothness of ride here is the amplitude of displacement of the cabin. That might not be necessarily the best measure of the smoothness of the ride. Another caveat before you go attempt this in your own car over a washboard road is that we are treating this as a quarter car model. So we're saying that the entire vehicle only has vertical displacement. But in an actual vehicle, we definitely would have to be worried about the pitch of the vehicle and possibly the roll. Now, the roll may be not a big deal if the washboard road is sufficiently wide. However, we're making the assumption that the entire car is going to have the same vertical displacement, and that's not going to be the case. So we would want to go into probably at least a 2 degree of freedom model over the same system before we make that decision. Also, this is specific to this car over a road with this wavelength. So we would need to consider other wavelengths before we do this. And finally, this is talking about a washboard road where we have this sinusoidal curve where we're going up and we're going down around some average 0 point. So this does not apply to going over something like a speed bump where that would be kind of a half sine wave where it's going to go up and then going to be flat at 0. It's going to go up and flat at 0. So we don't want to assume that we should go fast over speed bumps for a smoother ride because that is a different input than we have here. That is not simple harmonic displacement. A half sine wave we'll get into in the next section talking about general forcing.